Hi, this is Dane Quinn from the University of Akron. Today I would like to do an example dealing with planar dynamics. So we have a bar of mass m and length L as shown in the figure. So the point A is connected to a massless block and is constrained to slide horizontally in this slot, while the other end of the bar at B is connected to this massless block and slides vertically in the slot shown. I will apply a force minus F in the I direction, so the force is to the left, to the block A, and then I'd like to find the resulting angular acceleration of the bar if it's released from rest at some angle theta. So here, let's begin by looking at the system, and in particular the forces that act on this bar. So we have the weight, certainly. We'll label that as W. So the weight is one force that acts on the bar. And then we have reaction forces as well. And those will be at A. Here we're assuming that the reaction forces act directly at these pin joints. We'll label that as RA. And then we'll have a second reaction force at B, which we will label RB. And then finally, we have our applied load minus F in the I direction. And here, I and J are horizontal and vertical. And we'll define E1 and E2 to be along the bar. E2 is along the bar, E1 is perpendicular to the bar, so that E1 and E2 are oriented by the angle theta. So in addition to the weight, we have reaction forces and the external force minus F in the I direction. So these are all the forces that act on this bar. And so now I would like to identify coordinates and directions. Here we have the bar, and we will label several points. One of those will be the mass center, G. Then we'll label A and B as the blocks. And the line of action for these pin joints at the ends I've shown by these thin solid lines. And we'll denote the place that they meet as O. So that's kind of the corner of those slots. Now, the problem statement gave us one coordinate. In particular, it gave us the angle theta. But in addition, because of the constraints at A, we will identify the displacement of A as x, and likewise, we'll identify the displacement of B as y. Here we have these three coordinates, and in terms of the directions that were given in the problem statement, I and J, and then E1 and E2, we can express these directions. E1 in terms of I and J is cosine of theta in the I direction and sine of theta in the J direction, while E2 will be minus sine of theta in the I direction plus cosine of theta in the J direction. Now, again, the blocks are constrained so that the acceleration of point A is x double dot in the I direction, while the acceleration of B is y double dot in the J direction. However, this is a single degree of freedom system, which means we really only need one coordinate to identify the configuration of this bar. So x and y can be related to theta, or theta and y can be related to x. Y could determine x and theta. We need only one coordinate to describe where this system is. So the other two are related to the one that we choose. We'll express those constraints in terms of the kinematics. So again, notice that A is constrained and B is constrained, so we can relate the accelerations of those 2 points. and we'll write the acceleration of b is equal to the acceleration of a plus the angular acceleration of the bar cross r of b with respect to a, and then omega cross r. These are our equations for planar kinematics to relate accelerations. Now, the problem statement said that the bar was released from rest, which implies that the angular velocity of the bar is equal to 0 at this instant. As a result, this last term drops out. But we still have the remainder of these terms. So, filling in what we know, the acceleration of b was y double dot in the j direction. The acceleration of a was given as x double dot in the I direction. And then with this angle theta defined as shown, the angular acceleration of the bar is theta double dot in the k direction. And finally, the position of b with respect to a is L in the E2 direction. As a result, the right-hand side becomes x double dot in the I direction. K cross E2 was minus E1, so we have minus L theta double dot in the E1 direction. Or, making use of our expression for E1, we see that in the I direction, the acceleration is x double dot minus L theta double dot cosine of theta. And then in the j direction, we have minus L theta double dot times sine theta j. So here we can take components. In the I direction we have 0. So solving the components in the I direction, we have 0 equals this quantity. So we can solve for x double dot in terms of theta double dot. Likewise, in the j direction, we immediately find that y double dot is equal to minus L theta double dot sine of theta. So again, we're able to take components in the I and j direction to relate these coordinates. At this point, I don't know what x double dot is, I don't know what y double dot is, I don't know what theta double dot is, but if I knew one of these, say theta double dot, then I could find the other two. When we apply equations of motion, we'll need the acceleration of the mass center. So the acceleration of the mass center is, and let's go back and just pick one of these. Let's pick A, and we'll write the acceleration of g in terms of the acceleration of A and the rotation. So we have the acceleration of A plus again the angular acceleration of the bar cross r of g with respect to A plus the angular velocity cross omega cross r of g with respect to A. Again, at this instant, the angular velocity is 0, so this whole term drops out. And we're left with x double dot in the I direction, theta double dot in the k direction, cross now L over 2 in the E2 direction. So we'll take this cross product and we'll make use of the expression for x double dot that we found previously. So over here, to show that the acceleration of g is L theta double dot cosine in the I direction, and then k cross E2 again is minus E1, so we have minus L theta double dot over 2 in the E1 direction. Once again, I can write this in terms of I and j because we have an expression for E1 given here in terms of the I and j directions. So now I can combine these two and I end up with the following. L over 2 theta double dot cosine in the I direction, And then in the j direction, I have minus L theta double dot over 2 sine of theta. So in particular, this term combines with the I component here to give me this. And then we pick up the j component simply from this second term. So now we're ready to go and construct the free body diagram. Remember, we had these forces identified. And so now let's go and actually specify what they are in terms of the directions. Again, the reaction force at A is unknown magnitude, but known direction. The external force is minus F in the I direction. The weight, minus mg in the j direction. And finally, at B, the reaction force has an unknown magnitude, but the direction is horizontal. And so again, this was point B, this is G, and this was A. So here we have a free body diagram. We have the forces listed as vectors with unknown magnitudes sometimes, directions as given, and now we're ready to apply momentum balance. So the equations of motion are sum of the forces equals mass times acceleration of the mass center. So now, simply filling in what we have previously, looking at the forces in the I direction, we have RB minus F. And then in the j direction, we have RA minus mg. And our acceleration was given before. So we have m times L theta double dot over 2 cosine of theta in the I direction, and minus L theta double dot over 2 sine of theta in the j direction. So that's linear momentum balance. Now, turning to angular momentum balance, we have the sum of the moments acting about the mass center is the moment of inertia of the bar about the mass center times the angular acceleration. So the right-hand side is ml squared over 12 times theta double dot in the k direction. Again, this is the moment of inertia of a bar about its center, and this was the angular acceleration that we identified. Now we need to identify the moment produced by these forces. So there's a moment acting from the reaction force at B, a moment from the reaction force at A, as well as a moment from the applied load, and the weight produces no moment because it acts directly through the mass center. So this overall moment, let's look at the moment produced by RA first. Here the moment arm is L over 2 sine of theta, and the moment is going to be in the plus k direction. The moment produced by these two forces I can write together as RB plus F times L over 2 cosine of theta, again all in the k direction. So we have the moment produced by RA, we have the moment produced by RB. Notice that that's going to be in the minus k direction. Likewise, the moment produced by the applied load is going to be in the minus k direction. And so we have an angular momentum balance. At this point, we need to take components. So we'll look at the I directions here, the j directions there, both of those from linear momentum balance. Then we'll take the k direction from angular momentum balance. So let's write those down. We have in the I direction, we had RB minus F equals ml theta double dot cosine of theta over 2. In the j direction, we had RA minus mg is minus ml theta double dot sine of theta over 2. And finally, from angular momentum balance, we have L sine of theta over 2 times RA minus L cosine of theta over 2, RB plus F equals ML squared over 12 times theta double dot. So notice that we have three equations, 1, 2, 3, and let's look at our unknowns. In particular, I'll identify RB as one unknown, and I'll color that green. So everywhere we have an RB, we'll turn that green. RA is a second unknown. Let's use red for that one. Then we have theta double dot. And for theta double dot, let's use pink. So essentially, these are our three unknowns in this problem. We have RA, we have RB, and we have theta double dot. So really, we just need to solve these three equations for the unknowns. Remember, we wanted the angular acceleration of the bar, so we ultimately want theta double dot. So really, we'll solve for RA and RB from these two equations. We'll introduce them here, and ultimately we'll solve for theta double dot. Right, so RA is mg minus ml sine of theta over 2 times theta double dot. RB is f plus ml cosine over 2 theta double dot. And I'll take those, use them in this equation to find that L sine theta over 2 times RA, which is mg minus ml sine theta over 2. There's theta double dot, our desired unknown. We have a second term here. So notice that I'll have RB, which is f plus this quantity, and then I have another f, so I'll just write that as 2f plus ml cosine over 2 theta double dot equals ml squared over 12 theta double dot. So here I'll take these terms that depend on theta double dot over on the left hand side. I'll move them to the right, and I will solve for theta double dot. So as a result, we can find the angular acceleration of the bar. And you can pause this and do all this algebra, and what you'll find is that theta double dot is 3 divided by ml times mg sine of theta over 2 minus f cosine of theta. So this is the angular acceleration. In addition, I can always go back, take this, and then determine the reaction forces. So if I do that, I find that RA is, and I've done a bit of algebra and simplification here, but ultimately you get 1 minus 3 sine squared over 4 times the weight plus a term that looks like 3 sine theta cosine theta over 2 times F. So the reaction force at A depends on the weight and the applied load. And that's kind of interesting because if I notice the original problem statement, the force F acted in the I direction, while the reaction force at A is in the J direction. So we have some coupling, even though this doesn't act in the J direction. Because of the dynamics, it influences the reaction force at this point. And then, likewise, we can solve for RB. And we find 3 sine cosine divided by 4 times the weight plus 1 minus 3 cosine squared now divided by 4 times the applied load. So now here I'll just do a little bit of analysis of this and kind of give you a feel for what happens. And I'd like to plot theta double dot versus F. And so here we'll kind of denote 0 at this level. And I'd like to know how this angular acceleration changes as I vary the applied load. If the applied load is equal to 0, then the acceleration of the bar reduces to 3g sine of theta over 2L. And as F increases, this value of theta double dot simply decreases linearly. So I can represent that as just a linear decrease in the angular acceleration. But in particular, I want to note where this crosses 0. If we look at theta double dot and ask when does that equal 0, I can solve for F. And that happens at a value of F that's equal to mg over 2 times tangent of theta. So that's the value of the force that causes the angular acceleration to vanish. In fact, if we were to solve simply a statics problem, this would represent the force needed to hold the bar at a steady position, so with no motion. Now, if F is small, sufficiently small, below this value, theta double dot is positive, which implies that the angular acceleration is counterclockwise, and the bar, if we released it from rest, would begin to move in a counterclockwise fashion, so point A would actually move out to the right. However, if F is large enough, theta double dot is negative, and the bar begins to move in a clockwise fashion, right? And this point A is pushed to the left. So again, we can do a little bit of analysis and kind of get a feel for what's going to happen to the system as we vary the applied load. So that's it. This is a kind of nice problem with planar dynamics. We've got constraints provided by those two blocks. We have rigid objects that undergo both rotation and translation. And we make use of all the different equations of motion that we have. So that's it. Thank you very much, and I will talk to you again.